Okay, I think we're all here. Oop, spoke too soon. No, wait a second. I see more people in this class than I remember. Oh, right, I'm here twice. Okay. Okay, so um, let's see. I am currently doing this via a very clumsy system where I can see your pictures over here, but I have pinned my own picture up here. Um, that way I can sort of see you, and when I make recordings, you'll be able to see what's on the blackboard. If anybody checked out the recording from Monday's class, you'll see that it was in gallery mode, which isn't going to be particularly helpful if you are trying to see what's on the blackboard. So I am going to have to shuffle screens around and see if I can do this in a slightly less clumsy manner so I can more or less be looking at you while a recording is being made. But in the meantime, I'm going to look over there at your faces just to see if you have any questions at any point. But in the meantime, recording's happening over here. Okay, so let's continue from where we left off last time. We were talking about solving very simple system of equations, two linear equations, two unknowns, basically the intersection of two straight lines. The last time, we saw that, say, an equation 3x plus, say, 2y equals 5. Well, let's make it 6. In R2 represented a straight line. In the xy plane. And, you know, way back in your Algebra 1 class in high school, you probably put that into slope-intercept form and figured out where it crossed the y-axis and, you know, what slope was, sketch that thing. Right now, I mean, we can look at this. We can see it crosses the x-axis at 2, crosses the y-axis at 3, and so it's just a straight line going downhill to the right. But it's just a straight line. So in R3, let's say we have a linear equation, x plus 2y plus 3z equals 6. What does that represent, graphically speaking?
A plane.
Right, this is a plane. We can do our best to sketch this. This probably is not the first time you've drawn 3 axes, each of which is supposed to be perpendicular to the other 2. We draw the axis coming out of the border that's sort of on a diagonal, trying to use perspective as best we can. We make this the x-axis, and this the y-axis, and the up and down becomes our z-axis. And this is what's called a right-handed coordinate system. If we put our index finger in the direction of the positive x-axis, so coming out of the blackboard, coming out of your page, and your middle finger pointing in the direction of the positive y-axis, then your thumb automatically, if you use your right hand, this is called a right-hand coordinate system, use your right hand, then your thumb is automatically pointing in the direction of the positive z-axis. So positive x-axis, index finger, positive y-axis, your middle finger, and positive z-axis is your thumb automatically. So if you have done this sort of thing before, we can see that this thing crosses the x-axis. If y and z are both 0, this thing crosses the x-axis at 6. 1, 2, 3, 4, 5, 6. Crosses the x-axis right there. Crosses the y-axis if x and z are both 0. Then 2y equals 6. It crosses the y-axis at 3. 1, 2, 3. And it crosses the z-axis. If x and y are both 0, 3z equals 6, so z equals 2. And a neat little way to graph this thing is just connect these 3 points where it crosses the 3 axes. You have a picture that looks a little like that. You can see that that's just a piece of the plane which crosses, oops. That's a piece of the plane, which a plane, like a line goes on infinitely in both directions. A plane goes on infinitely in all directions. And what we're just seeing is one little triangle of that plane. This is where it crosses the YZ plane, the YZ coordinate plane. This line is where it crosses the XZ coordinate plane. And this line is where it crosses the XY coordinate plane. The XY is going to be like the sea level plane, the horizontal plane. And XZ and YZ are both vertical planes. So this represents a straight line. This represents a plane. If I gave you a system of equations, 3x plus 2y equals 6, and let's say x minus y equals, how about equals 1, we can see that this is the intersection of two straight lines. That's when we solve this, what we're looking at is something which solves this first equation, so anything on that straight line, and this is anything on this straight line. So x minus y equals, oh, I guess I drew that wrong, didn't I? Yeah, I did. I drew this equation wrong. This would cross. Oh, let me just change the equation. X minus y equals -1. Now it's right. We're looking for the intersection right here. If I give you, say, a set of 3 equations in R3, x plus 2y plus 3z equals 6. Let's say 2x minus y plus z equals 4, and let's say, I'm just making these up, x minus 2y plus 0z equals 1. What I have there is 3 different planes. If those planes all go through the same point, so if you can imagine two planes that are not parallel are going to cross a line. A third plane, if that third plane is not parallel to that line where the first 2 planes cross, and those 3 planes are going to cross in a point. And so I would have the intersection of 3 planes. So you could visualize this as the intersection of 3 planes. You could visualize this as the intersection of 2 lines. Okay. Now, if we solve something like this, or if we solve something like this, there's a question of how many solutions does a system of linear equations have? And actually, you can see all the different possibilities with just one linear equation and one unknown. So consider a single linear equation in one variable. Let's make it, let's call it x. Let's talk about some possibilities. How about the equation 2x equals 4? Yeah, let me make it 2x equals 6. Just so things don't get too confusing. How many solutions does that equation have? I promise I am not trying to insult your intelligence. Right, just one, right? You divide both sides by 2, x equals 3. That's right. Please believe I am not trying to solve. How about this one? 0x equals 3. How many solutions? So this had one solution. How many solutions does that second equation have? Any? Is there anything I can plug in for x that makes that? No, there's nothing I can plug in for x that makes 0x equal 3. 0 times x is equal to 0. I don't care what x is. 0 times x is not 3. So this has no solutions. This had 1. This has none. How about 0 times x equals 0? How many solutions does that have?
Infinitely many?
Yeah, it has infinitely many. Infinitely many solutions. Any value of x will make that true. The number of solutions here is all of r. That's the set of solutions. It's any real number will work because 0 times 5 equals 0, 0 times -7 equals 0. Any x will work. Any real x will work. And these are the 3 sets of possibilities. So a system of linear equations will have either one solution, so one unique solution, or no solutions, or infinitely many solutions. We'll have one unique solution, or no solutions, or infinitely many solutions. Those are the only 3 possibilities. So, given a system of equations, system of linear equations, we can ask about existence of solutions. This says, is there at least one solution? In other words, is the system consistent? Remember, we taught you in high school or middle school, you would have asked, is this system consistent or is it inconsistent? It's inconsistent if there's no solutions. You can also ask about uniqueness. So I'm going to underline existence, and I'm going to underline uniqueness. Uniqueness means, is there at most one solution? Yeah. So is there at least one solution? Is there at most one solution? If we have both existence and uniqueness, if there is at least one solution and there is at most one solution, what can you tell me? If there's at least one and at most one, how many are there?
One.
Good. Yeah, there's exactly one solution. So we say a system has a solution is both exists and is unique if there's exactly one. So a system, let me say, solutions to a system are exist and are unique. If there is exactly one solution. A system with no solutions is unique, but doesn't pass existence. And a system with infinitely many solutions passes existence, but is not unique. So the question is, how can we answer questions about existence and uniqueness? I want to introduce matrix notation. Let's say I have the system 3x plus 2y equals 7, and x minus y equals -1. This is the system written as a system of linear equations. The equivalent matrix would look like this. You just take the coefficients, 3, 2, and where the equal signs are, I'm going to put a vertical bar. Your textbook leaves that out. I'm going to put it in. I think it makes it clearer. If you would prefer to leave it out, that's fine. But just note that I am not using exactly the same notation as the textbook. So 3, 2, and then I'll put my 7 over here. And what I have in front of the x is an invisible 1, so that's what goes here. What I have in front of the y is an invisible -1. And of course, over here, I have a very visible -1. And so this system, written in linear equations, so this is a system of linear equations, has this equivalent notation. And as far as we're concerned right now, this is just shorthand for this. So you don't have to write the x's and the y's and the equal signs. We'll have another way of thinking about it later. What we have right here, the whole thing, is called an augmented matrix. If I just take the part to the left of the equal sign, remember that vertical bar stands for these two equal signs. If I just take this part right here, the 3, the 2, the 1, the -1, this is called the coefficient matrix. And right away, I hope this is going to be easy for you, even if these names, augmented matrix, coefficient matrix, if that's new, hopefully what should be easy for you is just to see a system of linear equations like this and being able to just say, oh, if I want to write this in matrix form, I'm just going to take the 3 and the 2, they go there, and take the 7, it goes there, vertical bar. If you want to put the vertical bar in, I think it helps. 1, there's an invisible 1 in front of the x, an invisible -1 in front of the y, and the -1. So you should be able to take this and write that. You should be able to take that and write this. They should be synonymous in your mind. It's like going back and forth between, well, this is, I was going to say between block text and script, but I know over the past decade or two, script has been de-emphasized in school. But you should be able to translate easily between these two forms. It should be a piece of cake. It should, you know, you don't even have to, you shouldn't break a sweat at all. Is everybody okay with going back and forth between those two forms? That part should be easy. Now, remember, to solve a system of linear equations, we did a sequence of elementary row operations. I didn't introduce this phrase last time, but I'm going to now. Elementary row operations on the system, trying to get the system in the form x equals some number and y equals some number. If we know what x is, we know what y is, we know where these two lines cross. I want to do the same thing. Instead of working with a system of linear equations where I have to keep writing the x's every time and the y's every time and the equal signs every time, I want to do it with the matrix form. Now, I want to remind you of the 3 kinds of elementary row operations that are allowed. And I want to be very specific about these. I was specific last time, but I want to hammer this idea in. So 3 elementary row operations. I think I'm going to need a elementary row operations. as follows. One, your book calls this replacement. Replace an equation or replace a row. Each one of these rows is just basically one of these equations. Replace a row by itself plus or minus a multiple of another row. That's probably the easiest one to get wrong. Secondly, I'm going to recopy this over here because I'm going to need it. 3, 2, 7, 1, negative 1, negative 1. I can remember that. I'm going to call the second one scaling. Multiply a row by a non-zero number. Third, what's your book called, this one? Not that the name really matters, but might as well just use whatever terminology they're using. Interchange. Works for me. Flip 2 rows. So if I had the system that I had before, which was 3x plus 2y equals 7, and I had x minus y equals negative 1, and we already had this in matrix form. 3, 2, vertical bar, 7, 1, negative 1, negative 1. Instead of working with these two equations, equation number 1, equation number 2, I can just work with the matrix that I have over here, each time doing one row operation.
Can you repeat what number 2 says? It says scaling.
Scaling, multiply a row by a non-zero number.
Okay. Thank you.
No, thank you for asking. Yeah, always, many of you have had me in multiple courses, you know that my handwriting may not be my strongest suit, and I try to straddle the line between legibility and illegibility. Whenever I dip below that line, please let me know right away. So remember, I'm trying to get x equals some number and y equals some number eventually. So that means I'm trying to get, so this is my goal. X equals something, y equals something, some number, some other number. That may not always be possible. But if it is, what I'm trying to get is a 1 up here, x plus 0y. So this says x plus 0y equals some number. And I'm trying to get 0x plus 1y equals some number. And if I do that, I have x equals whatever number's right there, and y equals whatever number right there. That's my goal. So let's start off with the matrix that I have, 3, 2, 7, 1, negative 1, negative 1. 3, 2, 7, oops, 7, 1, negative 1, negative 1. I'm going to put the vertical bar right there. And I want to try to get a 1 in the upper left-hand corner. There are multiple ways I could do that. I could take that first row and multiply by a third, right? I could take the first row and multiply by a third. If I took this whole row and multiplied by a third, I'd have a third times 3, which is 1, which is what I want there. I want a 1 right here, because that would be x. And I'd have 2/3 and 7/3. I mean, the downside of this is I have a bunch of thirds floating around. What's another way I could get a 1 in the upper left-hand corner?
Interchanging the
Interchange rows. I already got a 1 right there. I might as well just flip it up here. So I'm going to interchange the 2 rows. 1, -1, -1, and 3, 2, 7. Now I have my first goal. I have a 1 right there. I've interchanged 2 rows. Now let's keep going. I want to get a 0 below that 1. I want to get a 0 below that 1. So what I'm going to do is I'm going to take the second row and subtract off 3 times the first row. That's that replacement. So I'll take row number 2 and subtract off 3 times row number 1. So I haven't done anything to the first row. It's still 1, -1, -1. But I'm going to take row 2 over here, and subtract off 3 times the first row. So 3 minus 3 times 1 is 0. That's what I wanted. I wanted a 0 there. Now I have that 0 that I have right here. If I take 2 and subtract 3 times -1, that's 2 minus 3 times -1. 2 plus 3 is 5. And 7 minus 3 times -1 is 7 plus 3, that's 10. All I've done is I've taken row 2, each of these elements in row 2, and subtracted off 3 times the corresponding element in row 1. And I've created the 0 right there. Now I have this 1, I have this 0. I'd really like this to be a 1. How can I turn that into a 1 now?
divide the row by 5.
Yeah, so multiply the row by a 5th.
Yeah.
Yeah, I mean, but what you said is totally right. But when we talk about scaling, we multiply by a non-zero number. So we'll multiply the row by a 5th. But what you said is completely right. We divide the row by 5. But I'm going to write it as 1/5 times row 2. So 1/5 times row 2. So I've left row number 1 alone. 1, -1, -1. And I'm going to take row number 2 and multiply each element by 1/5. So that's 0. 5 times a 5th. 5 divided by 5 is 1. 10 divided by 5, 10 times a 5th is 2. Now I've got this the way I want it. I've got this the way I want it. I got this the way I want it. Remember, we're looking to have x equals something, y equals something. So 1, 0, 0, 1. That's what we're hoping for.
Oh,
Yes, question. Okay, so the only thing that we don't have yet is the 0 that we want up here. How can I make this a 0? How can I make that a 0 using one of my row operations? Leaving that a 1. I want to keep that a 1.
But you can replace it by adding the bottom one to
Yeah, we'll replace the first row with the first row plus 1 times the second row. So I haven't done anything to the second row. It's 0, 1, 2 still. But I've replaced the first row by the first row plus 1 times the second row. 1 plus 1 times 0 is 1. -1 plus 1 times 1 is 0. Now I've got this the way I want it. And notice the left-hand side looks exactly like what I want. X equals a number, Y equals a number. And -1 plus 1 times 2 is 1. So this just says 1 times X equals 1. So X equals 1. And this says 1 times Y equals 2. So this says Y equals 2. Instead of doing row operations on the system of linear equations the whole time, I just used the matrix form and did elementary row operations on that. I did 1, 2, 3, 4 elementary row operations to transform this coefficient matrix into the coefficient matrix I wanted. This just says X plus 0, Y equals 1, X equals 1. And this says 0x plus Y equals 2. Y equals 2. Is everybody okay with that? Is there anything I can explain? Or does that more or less make sense? Thumbs up, thumbs down, vertical head motion. Awesome. Caroline, at first I thought that was a virtual background, but I see sun on you, so I think it's real.
No, I am outside.
That is cool. I was hoping maybe I could do one of my classes outside.
Oh yeah, it's a little hot. I think I wore jeans. It's a little hot out here today.
It is the best real virtual background I've ever seen. Okay, so is this good so far? And again, keep track of what we were doing. 3x plus 2y equals 7. That's just a straight line. 1 minus, x minus y equals -1. That's another straight line. Those two lines cross. Every single time we did a row operation, we replaced one of those lines with a different line, but we didn't change the crossing at all. And finally, we have the line x equals 1, which is a vertical line at 1, and y equals 2, which is a horizontal line at 2, and they cross at exactly the same place that the original lines crossed. Is that okay? Let's try a different one. Restart it. X plus 2y equals 1. 2x plus 4y equals 3. Let's convert this into a matrix form. So right now I have 1 in front of my x, 2 in front of my y, equal sign, 1, 2 in front of my x, 4 in front of my y, equal sign, equals 3. And let's try to massage this into a form that looks something like that. Well, this is a particularly nice one in some ways. I already have a 1 in the upper left-hand corner. That part's already done, check. Let's get a 0 below it. So How can I get a 0 in the second row? I'm going to leave the first row alone for now. 1, 2, 1. How can I get a 0 right there?
If you do the second row and then subtract 2 times the first row.
Second row is 2 times the first.
Is that right?
Yeah, that's absolutely right. That's absolutely right. Somebody asked me a question? Oh, it's just some background noise. Okay, so second row minus 2 times the first row. So this 2 minus 2 times 1 is 0. That's good. 4 minus 2 times 2 is 0. That's weird. And then 3 minus 2 times 1 is 1. So remember, we were shooting for 1, 0, 0, 1. In this particular problem, we got the 1 here, we got the 0 here, but this became 0 at the same time. There's no way to get this into this form. If I change this into something that's not 0, this is going to go back to something that's not 0. Let's turn this back into a system of equations and see what we have here. We have 1x plus 2y equals 1. That's the same thing we had up here, which isn't surprising because we didn't do anything to the first row. And then we have 0x plus 0y equals 1. So that is the same thing as that. What can you tell me about that second equation?
No solution.
Yeah, there's no possible way to have any solutions to that. I don't care what x and y are. If you take 0 times x and 0 times y, you get 0, not 1. So as soon as you have a row which is all zeros to the left and a 1 to the right, or anything else besides 0 to the right, this has no solutions. So it's impossible to satisfy the second row, so it's impossible to satisfy the whole thing simultaneously. This has no solutions. And you can see that by the second row. You can see that as soon as you have a bunch of zeros on the left-hand side and a not 0 to the right of the equal sign, in any row, you're going to have no solutions. Now, what was going on in these original two, the original two equations? These are both lines, and there are no solutions. What kind of lines in the plane don't cross?
Parallel.
These are two parallel lines. Both of these lines have slope -0.5, but they're not right on top of each other. They're two separate lines. There are no solutions. So there we go. We found out there were no solutions as soon as we saw the 0, 0, and then a non-zero number. What am I doing? 5 minutes. Anything you can't do in 5 minutes probably isn't worth doing. How about I give you this example? Oops. How about x plus 2y equals 1 and 2x plus 4y equals 2? So let's turn this into a matrix, an augmented matrix. 1, 2, 1, 2, 4, 2. Again, that should be easy. We already have a 1 in that upper left-hand corner. That's good. We'd like to get a 0 below it. We'll do exactly the same thing you suggested last time. Leave the first row alone right now. 1, 2, vertical bar 1. I'll take the second row and subtract off 2 times the first row. So let's see. 2 minus 2 times 1, that's 0. 4 minus 2 times 2, that's 0. 2 minus 2 times 1, that's 0. Let me turn this back into equations. X plus 2y equals 1, and 0x plus 0y equals 0. Well, that second equation doesn't tell me very much, right? 0x plus 0y equals 0. That's true for any x and y. I don't care what x and y are. If you take 0, multiply it by the x, you take 0 and multiply it by the y, you get 0. So really, it just comes down to this first equation. How many solutions does that first equation have? How many points are on that line?
Infinite?
Every single point on this line, here we have a line with slope minus 1/2, crossing the y-axis at, what, 1/2, I guess. So this is 1, and this is 1. Crosses the x-axis at 1, crosses the y-axis at 1/2. It's just this line with slope minus 1/2. Sorry about my wonky line. Any point on this line, you know, a 0, 1/2, or 1, 0, or whatever point is right there, they all make this work, and everything makes that work. This was a line, this was a line. What can you tell me about these two lines?
Identical? They're
Right on top of the other. This line and that line are the same line. I just drew them twice. And so anything on that line is going to satisfy both equations. They are identical lines. This gets more complicated in higher dimensions, right? With lines, there aren't that many possibilities. Either the lines, you know, with lines, either when you're in R2, either they cross, or they're parallel, in which case there are no solutions, or they're right on top of each other, in which case there are infinitely many solutions. With planes in R3, or hyperplanes in R4 or R5 or R6, or in this course, we don't care if we're in R2 or R3 or R4 or R10 or R100. The basic principles are the same. It's just a little bit harder to visualize when you have more than 3 dimensions. You don't have to visualize. How are we doing? Is this making sense? Okay, I see I have 1 minute. I am going to give that 1 minute back to you. And so I will see you all next class. Oh, by the way, don't disappear quite yet. There was no homework for Monday. I think I may not post the homework until Friday, but keep an eye on it between now and then. As I said, there'll be about 1 homework a week. That's it. Bye, everyone.